Welcome everyone. In this video we are going to use Bernoulli's equation to find the speed of water that comes out of a water tower. And let me draw a water tower for you. So a water tower is something like this. You might have seen these in one of those cowboy movies, right? Cowboy movies. I really like a good cowboy movie. So maybe we have a water tower, it is providing water to a whole town. So it is quite important, especially in the old days. And we have a pipe that can go out of here, so it is flushing out of here. So we have our water, all blue. And the height of this water tower is going to be h. Notice that it is the height from the exit to the top, not from the ground, okay? You could also do that, but it doesn't really matter. So what I want to find is how fast will the water come out of this exit. That is V1. Actually, let's call V2 and you will understand why it is V2. What is V2? Well, as I said, we will be using Bernoulli's equation, which I derived in my previous video. You can find it from the cards right now. And if you do that, you know that that is a formula that relates pressure, velocity, and height values at different points of a fluid. Of a flowing fluid. So if we consider the top of our water tower as point 1 and the exit as 2, then using Bernoulli's equation we can say the pressure, let me write it here, P1, the pressure that is experienced on the first position, plus rho, which is the density of our liquid. And this is correct for fluids as well, but we are dealing with a liquid and water specifically. The fluid, the density times the g, gravitational field strength, gravitational acceleration, times h1, the first height, plus 1 over 2 rho v1 squared. And v1 is going to be the first velocity value, so it will be downward like this. Right, I hope this makes sense. Since water is coming out of the exit, the second position, then water should also move in the first position. I mean, the water should come from somewhere, right? It can't come out of nowhere, and it is coming from the position 1. This is equal to using Bernoulli's equation, only the subscripts will change. We have P2, pressure 2, times rho g h2 plus 1 over 2 rho v2 squared. Now, I want you to realize that this is a system that is open to the atmosphere. So, the pressure that we have on the first position is going to be P naught, which is the atmospheric pressure. It is basically 1 atm. Its value is not important, and its value, of course, changes, but generally we use it as 1 atm. So, as I said, it is open to pressure, and the pressure 1 then is equal to pressure 0, which is the atmospheric pressure. And the same thing is correct for the second position. It is also open to the atmosphere, so we have the same pressure of 1 atm at our second position as well. Which means P1 is equal to P2, and these are both equal to P naught, the atmospheric pressure. So we can make this substitution. For P naught, for P1, I am going to write P naught. Then we're going to have a plus. Well, what is H1? What is the height 1? If I choose my zero line as this point, as the level of my exit, if I choose this as H is equal to 0, then H1 is simply going to be height, the H. So we will have rho GH plus 1 over 2 rho v1 squared. We don't substitute for this right now. This is equal to, as I argued, P2 is equal to the atmospheric pressure, so we substitute P naught. Then we have a plus. Well, think about this. We have rho g h2. What is h2? We chose it specifically to be 0. We set our initial height value there. If we were to choose the ground as the 0 level, nothing would have changed, and you can try and convince yourself that nothing would have changed. And how do I know what nothing would change? Then this height value would also differ, it will be different, and it will cancel the height that comes from this part, and we would be left with this guy only. Okay, and I really want you to try to convince yourself if this doesn't make sense to you. Then we have, as I said, this is going to be 0. That is how we chose it. And even if we didn't choose it like that, we still would get the same value. Only this height term would remain. And then plus we have 1 over 2 rho v2 squared. And obviously we don't want to substitute for v2 because that is exactly what we are trying to find. We realize that p naughts cancel, so the atmospheric pressure does not matter. Wherever you do this, the atmosphere doesn't have an effect. Okay, you could even do this in the Mars, I think, or in the moon. Only the g's would change though, okay? So we got that out of the way, and also we notice another nice thing. We see that the rho's cancel, right? It is a common factor, so we can simplify by it. This means that what liquid or what fluid we have inside this water tower doesn't matter. If we were to have another fluid rather than water, we would still get the same result. And now let me solve this for v2 actually, v2 squared. We will have that v2 squared is equal to, if we multiply both sides by 2 to get rid of this 1 over 2 factor, we will have 2gh plus 1 over v2 squared. And here I claim that we can make an approximation. I claim that we can take this v1 squared to 0. And why is that? I mean, it is clear that it isn't exactly equal to 0 because water levels should be decreasing at the top of our water tower. But realize this, we have a very tiny exit here. This is a very tiny exit. And this is huge. If you ever saw a water tower in one of the movies, in one of the cowboy movies, or in real life, you know that it is a huge tower. It has a very big cross-sectional area, and the exit will have a very little cross-sectional area. So the water level will be decreasing very, very slowly at the top of our entrance. That is why we can make an approximation and assume that V1 is equal to 0. As I said, it is not equal to 0, not exactly, but we can simplify the situation. And if we make that simplification, we will get V2, and that's not a nice looking V, we get that V2 is equal to the square root of 2gh. And also you can convince yourself that we can make this substitution by considering that V1 is a small value, and if you take the square of a small value, you get something even smaller, right? If you take a square of a number between 0 and 1 or between -1 and 0, it is smaller than itself, right? If you, for example, consider 0.5. If you square this, this is equal to 0.25, which is less than the initial value. So V1 is a small value, and if it is between 0 and 1, well, then when we square it, it is even smaller. So maybe that might help you to convince yourself that this simplification is actually fine. And this is our result. We found a formula for V2. It turns out that it is a very simple formula. It is the square root of 2 times g times h. And you can check that the units work. We have g, which is in meters per second squared, meters per square seconds, and then we have height, which is meters. We have meters squared divided by seconds squared under the square root, so we get meters per second, which is a unit for velocity. And I also want to point out that this is the same formula for speed that you would get if you were to release a ball, let's say, from height h. You would get the same velocity. And how do I know this? Well, think of it like using the conservation of energy, for example. We could say it has an initial energy of mgh, the gravitational potential energy, and I derive the formula for this. You can access it from the card right now. This is equal to its final velocity here. It's kinetic energy, I mean, excuse me. And the kinetic energy is 1 over 2 mv squared. We see that masses cancel, so we get that v is equal to 2gh under the square root. And as you can see, this is the exact same formula that we just got. So it is kind of releasing a ball from rest, from a height of h, and you get the same velocity in the water tower case. So if you ever need to memorize this equation, you can keep that in mind by considering that other case. Or I would never encourage you to memorize this. This is a very quick calculation that you can make even quicker if you get comfortable with Bernoulli's equation and the idea of manipulating equations and making approximations. So I really encourage you to understand this and comprehend and convince yourself that this is a correct formula. Anyways, I hope this was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.